So today, we're going to tackle a really crucial concept you'll definitely see on there: minimum spanning trees. Let's crack this thing.
So before we get all theoretical, let's think about a real-world problem. I mean, this is something computer science is solving all around us every single day. Just imagine you've got a bunch of points you need to connect. Maybe they're cities on a map, or houses in a neighborhood, or even servers in a data center. The fundamental question is always, what's the absolute cheapest way to link them all up?
You know, whether we're talking about building roads, rolling out an electrical grid, or laying down fiber optic cables, the goal never changes. We need to connect everything, but we want to do it using the least amount of material, the lowest possible cost, the minimum effort. That right there, that's the core problem we're going to solve today.
And the formal, kind of elegant solution that computer science gives us for this exact problem, well, we call it a minimum spanning tree, or you'll usually hear us just say MST.
Okay, now this is important, so listen up. For your exam, you've got to know this definition inside and out. A proper minimum spanning tree has to check 3 boxes. First, it has to span the graph, which just means it connects every single dot. Second, it has to be a tree, and in graph theory, that means absolutely no loops, no cycles. And third, it has to be minimum. The total cost of all the connections, we call that the weight, has to be the lowest you can possibly get. If you miss even one of these rules, you haven't found the best solution.
Okay, so how do we actually find one of these things? Let's look at our first method, which is Prim's algorithm. I like to think of this one as the greedy grower, and you'll see why in a second. The whole idea behind Prim's is that it starts small and grows outward. Imagine you just pick any random node to start with. That's your seed. From that seed, the algorithm grows by always, and I mean always, picking the single cheapest connection to a node it hasn't visited yet. It's all about that methodical, one edge at a time growth.
All right, let's walk through our little example here. Let's say we start at node A. We look at our options. We can connect to node B for a cost of 1, or we can connect to node C for a cost of 4. So what's the cheapest first move we can make?
Right. Since Prim's is a greedy algorithm, it doesn't think ahead. It just looks at the immediate options and picks the cheapest one right now. And that's obviously the edge to B, with a weight of 1. So boom, we add it. Our little tree now includes nodes A and B.
Okay, step 1 is done. Our tree has expanded. Now, here's the key. We have to look at all the edges leaving our current tree. So we look at edges leaving from A and from B to any node we haven't visited yet. Okay, so from A, we can still get to C for a cost of 4, but from our new node B, we could get to C for a cost of 2 or to D for a cost of 5. So looking at all those options, the 4, the 2, and the 5, what's the cheapest next step?
Yep, it's the edge from B to C, with a weight of 2. It's cheaper than the other options, so we take it. And see, this is that growing process in action. Our tree now covers A, B, and C.
We're almost there. The only node left is D. So again, we look at all the edges leaving our current tree, A, B, C, that go to an unvisited node. The cheapest one is from C to D with a cost of 3. We add that edge, and we're done. Every node is connected, there are no loops, and we've got our MST. The total cost is just 1 plus 2 plus 3, which gives us 6.
Okay, another key thing for the exam: time complexity. If you use a clever data structure like a min heap to keep track of the cheapest next edge, Prim's runs in what we call O of E log V time. Now, what does that actually mean? Basically, it's really efficient on dense graphs. Graphs that are super interconnected with tons of edges. That's where Prim's really shines.
All right, so that's Prim's. Now let's switch gears and look at our second method, Kruskal's algorithm. If Prim's was our greedy grower, you can think of Kruskal's as the global bargain hunter. It approaches the problem in a totally different way. See, Kruskal's doesn't start in one spot and grow. No, the very first thing it does is look at every single edge in the entire graph, all at once. And it sorts them in a big list from the cheapest to the most expensive. It wants to know all the best deals before it does anything else.
So once we have that sorted list, we just go down it one by one. First up, the cheapest edge in the whole graph, A to B, cost 1. We'll take it. What's next? B to C, cost 2. Great, add it in. And after that, C to D, cost 3. We'll add that one too. So you see what's happening? We're not growing one single tree. We're building up a collection of little connections, like a forest of tiny trees that will eventually link together.
Okay, now we've hit the next edge on our list, and this is where a lot of students make a mistake, so really focus here. The next cheapest edge is A to C with a weight of 4. Now, based on the rules, should we add this edge? What do you think?
No, absolutely not. And here's the crucial part. If you look at our graph,
A and C are already connected. You can get from A to B and then from B to C. So if we added that direct AC edge, we'd create a loop, a cycle. That's redundant. It doesn't connect any new nodes, it just adds extra cost. So we throw it out, we skip it, and move on. That step, checking for cycles, is the absolute soul of Kruskal's algorithm.
And what about time complexity for Kruskals? Well, it's OE log E. The reason is pretty straightforward. The most expensive thing we do is that very first step, sorting all the edges. Everything after that is pretty fast. And this is why Kruskals is fantastic for sparse graphs, graphs that don't have a lot of edges. Fewer edges means a shorter list to sort, which means it runs faster. So there you have it, two totally different approaches, the grower and the bargain hunter. But look, they gave us the exact same minimum spanning tree with the same cost. So the big question, and this is definitely an exam question, is how do you know which one to use?
This little table really breaks it down nicely. The strategies are just completely different. Prim's grows out from one starting point. Kruskal's connects the cheapest bits and pieces all over the graph and merges them later. And that core difference in strategy is exactly why their performance changes based on the graph. Prim's is your go-to for dense graphs with lots of edges, while Kruskal's is the winner for sparse graphs with fewer edges.
And if you need a simple way to remember that, just think of this analogy. Prim's is like building a city's road network, starting from the center and slowly expanding outwards into the suburbs. Kruskal's, on the other hand, is like building the interstate highway system. You first connect major cities with those long, cheap stretches of road, no matter where they are, and eventually the whole country gets linked up.
Okay, let's boil this all down. We've covered a lot. If you're doing some last-minute revision for the exam, these are the key things you absolutely have to remember. Memorize these 3 points. First, what an MST is. Connects all nodes, no cycles, minimum total cost. Got it. Second, Prim's algorithm. It grows from one spot. That makes it perfect for dense graphs. And third, Kruskal's algorithm. It sorts all the edges first. That's why it's your best bet for sparse graphs. If you know those 3 things, you're in great shape. And really, that's the essence of minimum spanning trees. It's pretty cool, right? Both are greedy approaches that, for this problem, magically lead to the perfect global solution. But that's not always the case in computer science. So as you keep studying, I'll leave you with a final thought to ponder. Can you think of any real-world situations where just making the best short-term, greedy choice at every step could lead to a terrible overall result? It's something to think about. All right, that's it for today. Good luck studying for that exam.